So as we continue, we have to take note that the relationship between the end forces denoted by Q and the end displacement denoted by U for the plane frame for the members of the plane frame can be established by essentially the same process as we used previously for the beam. So actually the process involves subjecting the members separately to each of the 6 end displacement and to the external loading with no end displacement, with both ends completely fixed against translation and rotation. So we have to take note that the total end forces due to the combined effect of the 6 displacement and the external load can be expressed by this equation, wherein you have Q's of I actually will be equivalent to, it can be expressed through this equation. So that will be the summation actually of K's of ij times Q's of j plus Q's of f, from wherein our I is from 1 to 6. However, in which our K here is our stiffness coefficient, which represents the force corresponding to Q's of I due to a unit value of the displacement, U's of j and Q's of f, which denotes the fixed end force corresponding to Q's of I, which is due to an external load acting on the member. So however, our equation can be expressed in this form. We have here for our Q, that can be equivalent to, as for every member, this is the formula for every member. This is Q is equal to, as we have to take note that for every member there are 6 member and the forces. So Q's of 1, Q's of 2, Q's of 3 at the beginning of the member, Q's of 4, Q's of 5, Q's of 6 at the end of the member. Equal that to our K and multiplied to our U, member end displacement, then plus our member fixed end forces, Q's of F. So our U is member end displacement, there will be 6 for every member, and our Q's of F, there will be also 6 member fixed end forces. And this will be the formula, the general formula, and you have to resolve this per member. So which means if you are on member 1, so you're going to have a member 1. If that is now member 2, you have to denote this as member 2. So, and so on and so forth. And this one can be expressed into this manner, wherein Q is equal to K times U plus Q's of F. So we have to take note that our K is our stiffness coefficient, our U is member end displacement, our Q's of F is member fixed end forces. And for our stiffness coefficient, our small letter K, which is in the local coordinate system, is equal to this equation. So we have to identify our modulus of elasticity, our moment of inertia, and of course the length of the member that you are solving, and of course the area for that particular member. So this is per member. So if you are in member 1, so you're going to have case of 1. If you are on member 2, that will be case of 2. And if there will be 6 members, so you will have to compute a 6K value. So this is now a six by six matrix for our K formula to compute for our stiffness coefficient in the local coordinate system. So how are we going to compute for our member fixed end forces, which is our Q's of F? So of course, for Q's of F, we have 6 member fixed end forces for every member. So actually, those are equivalent to, so we have here axial force, shear force, and moment force at the beginning of the member. So we have your small letter B to denote beginning of the member. Then axial force, shear force, and moment force at the end of the members. You have here E to denote at the end of the member. So basically, for our shear forces and moment forces, of course, we have to make use of the equations that we have introduced before. So please take note that for our axial force that is acting normal to the member, to to our structure, to each of the members. So for example, we have here a member. So this is our member. So this will be our axial forces. And if this will be our member, so this is our axial force. If this is our member, so that will be our axial force. So we have to take note that our axial force is acting normal to our member. So for our example, we have here the displaced position of member 2 of the frame as given in the figure is actually given in figure 6.6b. So that's displaced position of member 2. So calculate the end forces for this member in the local coordinate system. Is the member in equilibrium under these forces? So if you're going to observe class, this is our plane frame. So we are trying to solve for, we're going to evaluate member 2. So member 2 actually is inclined in position. So we have to, this is an inclined position. We're given with the parameters, our modulus of elasticity, our area, and our I. So our area is given. So modulus of elasticity is 29,000 KSI, area is 28.2 inches squared, and I is 833 inches to the fourth. And for the length of the member, since this is inclined, so we have to resolve, we have to compute. So by Pythagorean theorem, we have to compute this one. So this will be actually by Pythagorean theorem. So that will be, so this will be along x is 16 squared, along y is, this is 24 minus 12. So this gives us 12. So which means that we have here the square root of 16 squared plus 12 squared. So it's give us 20 feet or 240 inches. So we are given with the displaced position of our member 2. So we're given with our use of 1. We have our use of 2. This is our use of 3 at the beginning of the member. So this will be our use of 4, use of 5, and use of 6 at the end of the member for member 2. Now we have to identify our stiffness coefficient in the local coordinate system denoted by small letter k. This is for member 2. So using the formula, so we have here identified the equivalent value. And of course, we have to write our member end displacement for member 2 in matrix form. So based on the figure, so we simply have to translate that one into matrix form. So this is now the member end displacement for member 2. So these values are taken from the figure for the displaced position of member 2. This is our use of 1, use of 2, use of 3 for member at the beginning of the member. This is use of 4, use of 5, use of 6 at the end of the member for member 2. Now, for member 2, the external load or the load that is acting is a uniform loading. It has an intensity of 3 kips per feet. So, if you're going to observe, this is the, so we have here our uniform loading. So, the intensity here, this is member 2. The intensity is 3 kips per feet. So, if you're going to convert this one into inches, so that will be equivalent to, convert that to inches, this is now equivalent to 0.25 kips per inch. Now for that one, since this is an inclined position, so we're going to resolve this into components. So we're going to have our x component and our y component. So we have to take note that the slope for this, actually the slope is, this is, we have computed this one. So this is 3. So this is 4. This is 5. So which means that if we're going to have our W's of x, this is our x component for our uniformly distributed load for our member 2 rather. So that will be W's of x. So we have here negative 3 all over 5 times 0.25. And that will be equivalent to negative 0.15 kips per inch. And W sub y is 4 all over 5 times 0.25. So that will be 0.2 kips inch per inch. So for this one, for the negative, for the sign, so they try to, the author uses negative to indicate that it acts in the positive direction of the local x-axis. So it is dependent on the author. So the author uses a negative sign for w sub x, which indicates that it is acting in the positive direction of the local x-axis. So he just make use of negative to indicate that the force is acting on the positive direction of the local x-axis. Now for our axial force, you are going to make use of this equation for the computation of the axial force at the beginning of the member. So we simply have to identify the intensity for the intensity of the load that is acting, and at the end of the member, so we have here the formula at the end of the member. So basically we have here our L for the length of the member and our I, which has the moment of inertia for the member. So therefore, the axial force for member 2 at the beginning of and at the end of the member, so our W or omega, our omega, since axial force is, if this will be our member 2, this is our member 2, so which means that this is the position of our axial force F sub A. So which means that is acting normal to the position of the member. So now we have this is uniform loading, and we have resolved now our uniform loading into, since this is inclined, so we have resolved that into x and y components along horizontal and vertical direction. So which means that for our axial force at the beginning of the member and at the end of the member, they are equal. So for this one, we have to take note that axial force is in the along x direction. So we have resolved a while ago that our W sub x is equal to negative 0.15 kips per inch. So this will be the value for our omega. So you have negative 0.15 times the length, which is 240 all over 2. Since in the formula we have the presence of our I, but I sub 1 and I sub 2, but our I sub 1 and I sub 2 is equal to 0, so it was reduced, the equation was reduced. And if we try to simplify this one, so we have now negative 18 kips, so that is now the equivalent value. Because the formula actually a while ago is F sub A sub B is equal to omega all over 2L multiplied to L minus I sub 1 minus I sub 2. Then we try to multiply this one to L minus I sub 1 plus I sub 2. So we have canceled out our I since that is equal to 0. So it was simplified. So now we have our axial force at the beginning and at the end of the member. So that is the value, negative 18 kips. Now for our shear force and at the beginning at the end of the member, so we have to make use again the formula from our toss. So which means that this is WL all over 2. So that is simply have to substitute. So we got here a value of this is for the axial force actually that is acting in a vertical direction. So this is our shear force rather. For the shear force that is acting in the vertical direction, so that is W sub y. So W sub y we have computed that is equal to 0.2. So which means that 0.2 times 240 all over 2, we get a value of 24 kips, that is the shear force at the beginning and at the end of the member. Now for the moment force, of course, the formula is for the uniform loading from our toss is